So the exercise related to electromagnetic effect, and I'll discuss a structure question from this exercise related to the topic, the electromagnetic effect. Begin with question 17 onwards. Okay, question 18. Question 18 is the same concept like about the electromagnetic induction, that change in the magnetic field induces EMF. So we have a student is investigating, the student is investigating the law of electromagnetic induction. What is the law of electromagnetic induction, or according to electromagnetic induction? Whenever there is a change in the magnetic field, what it will do? It will induce or produce EMF. So when this bar magnet is dropped through the coil, there will be a change in the magnetic field and it will induce EMF. So when the bar magnet is moving towards, then according to the Lenz's law, EMF induced always oppose the change. So this side will be north and this side will be south. But when the bar magnet is moving away, opposite pole will induce. As a bar magnet move through this, it will, because the magnetic field is decreasing, so it will try to increase. And opposite pole will be there, so the direction of the induced EMF will change. And you can also see from the graph for induced EMF, and the time graph is there. As you can see, a bar magnet fall through a coil and EMF is induced. And why initial EMF is positive and then it is negative? If you remember that according to Lenz's law, induced EMF always oppose the change. Like the induced EMF is equals to minus delta N phi over delta T. When it is moving towards, like as I mentioned, magnetic field is increasing. So when we work out this final minus initial, that this value will be positive. So if this value is positive, because N phi means a change in a magnetic flux linkage. So when we take a final minus the initial, what we will get a positive answer. And this positive answer is multiplied with negative from the outside, like the part of a formula. That's why induced EMF was negative initially. But then when it is going out, what is happening to the strength of a magnetic field? The magnetic field strength is decreasing. So when we take this formula like minus delta N phi over delta T, so negative, the final as the final magnetic field is like it's decreasing or it is zero. So when we take N final minus initial, what we will get, this will be smaller, this will be larger. So the final answer is negative. And negative multiplied by negative, so it will become positive. That's why when it is moving towards, the induced EMF was negative. When it is going away, the induced EMF is positive. As you can see here, initially, this is a part. If we have a coil and it is the magnet is moving towards this, for this section is representing. But when the magnet is going away, the same magnet is moving away. This is a section which is representing the motion of the magnet. And you have to write the structure answer for this. Explain the shape of the graph, the 5-mark question. So first thing what we'll say about the electromagnetic induction, that the change in a magnetic field induces EMF. The change in magnetic field induces EMF. The magnitude of induced EMF depends on rate of change in magnetic flux linkage. So Whenever there is a change in magnetic field, that will induce EMF, and the magnitude of the induced EMF, like how much induced EMF produced, that depends on the rate at which the magnetic field is changing, or magnetic flux thing is changing. Then what happened? The second part. So, and then explanation of the graph. The induced EMF is increasing, as you can see the graph, because the speed of the falling magnet increases, which cause greater change in magnetic field. Then we have the Lenz law. According to a Lenz law, the induced EMF always oppose the change in magnetic field. So whenever there's an induced EMF, the induced EMF, what it will try to do, it will try to oppose the change in magnetic field. If a change in a magnetic field, if it is increasing, it will try to decrease. And if the magnetic field is decreasing, it will try to increase. So, and how we identify that the speed of a magnet is increasing, the positive value, if you compare the graph, the positive value is greater than negative value of voltage, or we can also say it take shorter time for the positive as compared to negative voltage. And the magnetic flux linkage is constant, which is area under the graph. So you can see the two graphs have the same area, which shows that the magnetic flux linkage is constant. Is it clear, this one? Any doubt in this?
No, sir. Clear.
A data logger was used in this experiment rather than a voltmeter. This is related. Describe a condition that make a data logger more suitable. Look, if we want to record simultaneous results, like if I want here, what we want to measure a voltage and we want to measure time. So we want to measure and simultaneously, like after 2 seconds, how much is the voltage, after 4 seconds, 6 seconds, and so on. So voltage and the time we have to measure simultaneously, and we want to record more values in a short time, or we want a greater sampling. So in that case, the data logger is more suitable as compared, because when we are using a voltmeter, we have and a stopwatch. In that case, we can have a limited, like after 10 seconds, we can measure a voltage. Let's say 5 volts was there. Then after 20 seconds, we measure another voltage. Let's say 8 volts was there. But if you are using a data logger, you will have more values within that time span. Like example, A data logger will measure 10 seconds, 11, 12, 13, 14, and so on. And same way, it will also shows the change, the variation in the quantity. Like let's say it was 5, 5.3, 5.9, 6.5, and so on. So we'll have range of the result as compared to having a few values. So the data logger is suitable if we want a high sampling rate. High sampling rate means like if I want to record more values in a short time, or if you want to measure two readings simultaneously, or if you want to carry out experiment for a longer duration of a time, that's also a data logger is suitable. And we can also just sit and in like record the values. We can also data logger is suitable to record the values remotely. Like you don't have to be next to the apparatus. The values will be recorded automatically. So these are the conditions in which we can use a data logger. Is it clear?
Yes, sir.
The next is question 19. A student places two magnets. As you can see, a student places two magnets on the holder so that the north pole of one magnet faces the south pole of the other. The arrangement was placed on a sensitive balance um, calibrated to measure force. The student held part a closed loop of a wire between the magnet as shown. When a student moved the wire quickly downward between the magnet, the reading of the balance changes. So there is no supply here. As you can see, there is no supply, but the reading on the balance changes. Why the reading on the balance changes? If we draw this, like let's say this is a magnet, and it is placed on the balance, and we move the wire, like this blue color is representing a wire. So when student move the wire quick downward, so student move this wire downward, why the reading on the balance changes? That is the question. So first thing, the wire does not have any power supply. So if the wire does not have any power supply, what does it mean? It means when we move the wire, there will be a change in the magnetic flux linkage, or magnetic flux, you can say. And change in magnetic flux induces what? It will induce EMF. And this induced EMF, the induced EMF or the current, it will produce an EMF, not a current, because the circuit is not complete. That's why we cannot say a current. Or if a circuit is complete, then we can say it's a current, as they did not represent the full. So as a result, when there's a change in magnetic field, it will induce EMF. And induced EMF always try to oppose the change. According to Lenz's law, it will always try to oppose the change in magnetic field. So if the magnetic field is increasing, it will try to decrease. And if a magnetic field is decreasing, it will try to increase. So if the wire, we are moving the wire downward. So which direction the force will be there to oppose the change? So there will be an upward force on the wire. Or there will be a down, because according to Newton's third law, forces always act in pair. So if there is an upward force on the wire by the magnetic field, there will be a downward force on the magnet by the wire. So what actually happened here, like you have a wire and which is placed in a magnetic field, you move the wire downward, means, and when you move the wire downward, the change in a magnetic field produces EMF. Because of this induced EMF, the EMF induced always try to oppose the change. So which direction, if the wire is going downward, so which direction the force will be there? Upward on the wire to oppose the change. And forces, according to Newton's third law, forces always act in pair. So if there's an upward force on the wire, So what will happen? There will be a force on the magnet, but which direction there will be a force on the magnet? The force on the magnet will be downward. And because of this downward force, the reading on the balance will increase and we can identify how much force is there or what is the magnitude of the downward force. Is it clear till this point?
Yes, sir.
So how you score the marks here? How you score the marks? A 6-mark question. First thing, when a wire is moved downward, there is a change in magnetic field which induces EMF, and the induced EMF always try to oppose. So there will be, because if the wire is moved downward, so the force on the wire will be upward to oppose its motion. And when there's an upward force on the wire, because of the changing magnetic field, there's an upward force on the wire. So forces always act in pair. So if there's an upward force on the wire, there will be a downward force on the magnet, because according to Newton's third law, forces act in pair, and the pair forces, the characteristic of the pair forces, they are same type, same magnitude, same line of action, acting at the same time, but acting in opposite direction, acting on two different objects. If one is a force on the wire, another one will be the force on the magnet. Is it clear, this one?
Yes, sir.
Then we have the part B, which is related to the calculation.